This video series is based on what I learned in school and the Princeton Review's AP Chemistry Premium Prep Book. I scored a 5 on the exam this year, but it wasn't always like that, okay? I used to get a bunch of 60s, 70s, B's, C's in my chem class. So when it came to studying for the AP exam, because nothing else was really working, I started explaining things to myself in a weird way, and in the end, it wasn't really about the 4 or the 5, but instead, it was about having fun. I hope that through this video, you can learn a different approach to chemistry, and that when it comes to the exam, you can ace it. And most importantly, have fun. Like me. Unit 1. In this unit, you dive into the periodic table, and you learn about electron configuration, a key rule called Coulomb's law, photoelectron spectroscopy, atomic structures, periodic trends, and mole-related ratios. So let's dive into the periodic table. I got this from PubChem. And if you've ever had an introductory chemistry class, you know the basic components of each element square in a periodic table. The top number tells you the number of protons in the element, so we know that helium has 2 protons. And what would usually be the bottom number has the average atomic mass of a single atom of that element. Helium's average atomic mass is 4 grams. If you don't remember, this is a rough drawing of an atom. Inside its nucleus are protons and neutrons, and outside are its electrons. Protons are positively charged, neutrons are neutral, and electrons are negatively charged. Quick test. What is the atomic mass? It is the number of protons and neutrons added together. This fake atom here would have an atomic mass of 2 grams. We said what's usually the bottom number is the average atomic mass. Now when I say average atomic mass, I mean that there are other isotopes, meaning atoms with the same number of protons but different number of neutrons that consequently add up to different masses. And when we get their averages, that's average atomic mass, or AMU. There are a few graphs that can show the relative abundance of isotopes. For example, this one for the strontium element. There are 4 bars of blue shown, with the x-axis representing atomic mass and the y-axis representing their relative abundances. Obviously, an isotope of strontium with a mass of 88 is the most abundant. To calculate the average atomic mass, however, all you need to do is multiply the abundances of each isotope and add them all together. For example, if we have 86 at 10%, we will convert 10% to a decimal. And we'll multiply 86 by 0.10, and then we'll add that for each bar that we have shown. Once we add them all together, we will have the average atomic mass of the element. Don't try to memorize the formula, it's pretty straightforward. Just think, you're getting a fraction of each isotope, a larger fraction of it if it's more abundant, and then adding all those fractions together to get the average. There are a few practice problems that can test your knowledge on average atomic mass. I pulled these from 2 different practice tests in Princeton Review. Take a look at the first one. This is a mass spectrum for zinc. What could we conclude from this graph? Well, the y-axis doesn't have tick marks, so I know it's not going to ask me for the exact average AMU, though if I wanted to, I could find it on the periodic table. A common mistake might be to pick B. Don't assume that because 64 and 66 were so abundant, 65 might be the estimate AMU. You cannot assume that with the percentages not even given and with the distribution shown in the mass spectrum currently. Instead, the 4 bars represent a sample of atoms with 4 different atomic masses, and that is the only thing you can correctly determine from the graph. Therefore, D is the correct answer. The next question is approached differently. This time, the correct answer is already shown. This answer is based off the actual average AMU. The graph shows exact percentages to base your answer off of. Calculating the AMU from our previous formula, I got 90. Based on the periodic table, I know zirconium has 40 protons. Recall that AMU is protons plus neutrons, so if we have 40 protons, we must have 50 neutrons. Therefore, D is the correct answer. What else should you know about the periodic table? Each column is called a group, and there are 8 groups we mainly focus on in AP Chem. 1, 2, 3, 4, 5, 6, 7, 8. If you're wondering what we just skipped over, they are our transition metals, and they differ in charge and have more special rules in electron configuration, which we will get to soon. Group 1 has 1 valence electron. Valence electron meaning outermost electron. Group 2 has 2, Group 3 has 3 valence electrons, and so on. Group 7 elements are halogens. This name, halogens, is worthy of memorizing, as some problems later on related to empirical formulas might say halogens instead of the actual element. Group 8 elements are what all the other atoms want to be like. They have a full octet, meaning all 8 valence electrons. This idea of having a full octet is really important in terms of understanding bonding, which is in Unit 2. Finally, groups 1 and 2 are metals. Other than that, I wouldn't stress too much about memorizing other names such as metalloids, alkali metals, alkaline earth metals, etc. In this part of the video, we'll first go over photoelectron spectroscopy, electron configuration, bonding, and then periodic trends. Let's talk about photoelectron spectroscopy and electron configuration. Electron configuration is how we represent the energy of electrons being quantized, meaning electrons can be on shells n equals 1 and n equals 2, but not n equals 1.5, just like stairs. The shells you see here represent the Bohr's model. It's not the best model, we'll later learn, but it's good for now. And as you go out, the shell number increases. Electrons can jump to higher levels if the atom absorbs energy. If the atom releases energy, its electrons drop to lower levels. And when we say the atom absorbs or releases energy, we mean it absorbs or releases energy in the form of electromagnetic radiation, which can come in different forms such as microwave, visible, UV, infrared, etc. Infrared radiation is used to study the vibrations of chemical bonds, while microwave, as you might guess from its name, is used to study the rotation of molecules. Keep that in mind for our practice problem later. It's useful to know that when a sample is hit with electromagnetic radiation, electrons can be freed. Let's take a look at one singular atom here. If I hit this sample with radiation, I could free electrons from the nucleus. I would have to hit it though with the amount of radiation that is its binding energy. If I hit it with 5 kapows and that electron was freed, 5 kapows is its binding energy. If I hit it with 8 kapows, I have 3 extra. Don't tell your teacher I use this terminology. Anyway, those 3 extra kapows become the electron's kinetic energy. So leftover energy after the binding energy is the kinetic energy. Since kinetic energy increases with mass and velocity, if I have more extra radiation, I'll have faster electrons. So here's a quick equation to sum it up. Radiation energy used on the sample equals binding energy plus the leftover energy, which is the kinetic energy of the electron. This photo of a photoelectron spectrum I got from Khan Academy shows all the binding energies for all electrons ejected from an atom's nucleus. The y-axis shows the number of electrons ejected from each level, and the x-axis shows binding energy, which is usually expressed in eV. Each eV is 1.6 times 10 to the negative 19 joules, but you don't need to know that. The x-axis increases right to left. You can think of this corner as the nucleus, so peaks closer to it represent electrons closer to the nucleus. If electrons are negatively charged and the nucleus is positively charged, these closer electrons are going to be harder to eject because they're attracted to the opposite charge. So, the electrons closer to the nucleus would also require the most binding energy to be ejected. Each group of peaks is one energy level, and within each level are subshells. This is especially relevant as we learn how to write electron configuration, which helps list out an element's shells, subshells, and orbitals. Now we can finally learn about electron configuration. From here, you're going to have to memorize a few labels. The first block on this periodic table is the S block or S subshell. Recall that if this is a shell, this is a subshell. This is the D subshell, and then from groups 3 to 8, is the P subshell. The only exception here is helium, which will be part of the S subshell. Then, the first row, or as we learned, the first period, represents the first energy level, n equals 1. The next is n equals 2, and so on. Now you just combine the letter S, D, or P with the number of the shell that it's in order to describe the location of any element on the periodic table. So here, this is in the S subshell, but it's also in n equals 1, so we write 1s. If we must pass 2 of these, then we'll write 1s with a 2 in the superscript. Let's try to write an electron configuration for helium. You first locate the element. We know that helium is in the S subshell, and it's in the shell n equals 1. So we will write down 1s. And because you had to hit 2 of them to get to helium, we will put a 2 in the superscript. Let's try it for lithium. Let's locate lithium. Electron configuration is almost cumulative. Just because you pass to the next energy level doesn't mean you erase the list from before. We must still hit 1s 2 times, so keep the 1s too. But you must also hit 2s once to get to lithium, so put 2s with a 1 in the superscript. This is the electron configuration for lithium. Let's try it for magnesium. So we still have to pass by 1s2, and we also have to pass by 2s1, but also another 2s. So that becomes 2s2, and then we have to keep going. So we'll have to pass by all of these as well. This is in the 2p subshell. So we'll write down 2p, and because we had to pass through 6 of these, we'll put a 6 in the superscript. Now we just have 2 more to take into account. This is in the 3s subshell. We have to hit 2 of them to get to magnesium. So we'll put a 2 in the superscript. This is the electron configuration for magnesium. Pause the video and try it yourself for argon. If you got 1s2, 2s2, 2p6, 3s2, 3p6, you are correct. If you're wondering about the D subshell, let's talk about it. Something unique about this is that when we look at the D subshell, after 4s, we see it says 3d. You should memorize this. So when we write electron configuration for something like iron being here, you should write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. It might be weird going from 4s2 to 3d6, but that's how it is with a D subshell. Easy so far, right? You will then have to be able to draw orbital diagrams, which goes along with an atom's electron configuration list we made before. For S, you're going to draw 1 box or 1 orbital. For P, you will draw 3 orbitals in 1 subshell. And for D, you will draw 5 orbitals in 1 subshell. Each orbital only gets 2 electrons, which you represent with 2 oppositely faced arrows. Let's do this for helium. Helium was 1s2. So draw the s orbital and put 2 electrons in it because of the superscript here. That was pretty easy. Let's try it for lithium. Lithium's electron configuration list was 1s2, 2s, 2s1. So draw 2 s orbitals. Fill the first one with 2 electrons, and the second one with only 1 electron. Let's try it for sulfur. You can go ahead and try to write the electron configuration for sulfur on your own. Sulfur's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Let's draw 2 s orbitals, 1 p subshell, which has 3 orbitals, 1 s subshell or orbital, and then another p subshell. This is matching the order of the electron configuration we have written here. Let's fill the first 2 s orbitals. Now, when it comes to filling the p orbital, make sure you fill each orbital with 1 electron each, and then go back to add another. This rule is called Hund's rule. So we'll first fill each orbital with 1 electron, and then go back for more. Let's fill up the rest until we get to 3p4. Now for 3p4, keep in mind Hund's rule. Make sure you fill each orbital with 1 electron first. So there should be 2 electrons in the first box. If you didn't use Hund's rule, you might have ended up with this instead for 3p4. So make sure to use this rule. So you just learned about binding energy, radiation, photoelectron spectra, electron configuration, and orbital diagrams. So let's do some practice problems together to solidify some of this in our brains. First, you will have to recall the earlier equation given about radiation and kinetic energy. Take a look at this photoelectron spectrum. You can label each as the following: 1s, 2s, 2p, 3s, 3p. Recall that how high a peak is represents the relative electrons in each orbital, so let's now add the superscripts to each subshell. So closer shells, closer to the nucleus that is, are going to require more binding energy than farther ones. Practice problem 3 asks, if an electron is ejected, which peak would it have to be ejected from to have the greatest velocity? The megajoule per mole is just another unit of energy, like EV. I hid the right answer, but what do you think it is? Pause the video and try to figure it out. If you got D, you're correct. Having the lowest binding energy means that there would be more kinetic energy left over, which would translate into the electron's velocity. Therefore, that electron would have the greatest velocity. Also, going back to the graph, you should be able to tell which element this is describing by looking at the electron configuration. If we ended at 3p3 and refer back to the periodic table, 1, 2, 3, we should end at phosphorus. So question 4 asks, how many valence electrons does this atom have? Phosphorus is in group 1, 2, 3, 4, 5, and if you recall correctly, this also means it has 5 valence electrons. So again, D is the correct answer. Speaking about binding energy and all, let's talk about Coulomb's law before we do one more practice problem for this section. Coulomb's law describes the attraction between opposite charges. The attraction between opposite charges is also called electrostatic force. Remember this term so that you can use it in the FRQs. How strong this electrostatic force is calculated using Coulomb's law, but you won't need to know how to calculate it for the AP exam. You will only need to know how to use the variables in Coulomb's law to explain trends. The law looks like this. The F with coulombic in its subscript represents the electrostatic force between the nucleus of an atom and its electron, and how strong it's going to be relative to the other variables. Remember that the nucleus is positively charged and the electron is negatively charged, hence electrostatic or oppositely charged. Q1 means the magnitude of the positive charge, and Q2 is the magnitude of the negative charge. R squared represents the distance between the electrons and nucleus squared. So the strength of the force is inversely proportional to the distance. So the larger the distance between the electrons and the nucleus, the weaker the force. Why is that? Well, let's think about it the opposite way. The shorter the distance is, the electrons are closer to the nucleus and also more attracted to its opposite charge. The force is directly proportional to charge, however, so the greater the magnitude of any or both of the charges, the greater the force. This is because the more protons or more positively charged the nucleus is, wouldn't the electrons be more attracted to it? We talk about attraction in Coulomb's law, but in the reverse way, just as we talked before about binding energy, that same electrostatic attraction must also be overcome if we wanted to remove an electron. Okay, now we'll move on to the last practice problem of the section. Let's see if you remember this. So another popular question in AP curriculum is, if you wanted to study blank, what radiation would you want to use? So, if you wanted to study the vibration of bonds, what radiation would you want to use? If you said infrared, you are correct. If you wanted to study the rotation of molecules, you would use microwave radiation. Now we have wrapped up binding energy, radiation, photoelectron spectra, electron configuration, and orbital diagrams nicely. But that's not all of Unit 1. We learn about Coulomb's law, and we still need to talk about the periodic trends, but we'll pair this with Unit 2 bonding to make it stick better in our brains. So let's talk about the basics of bonding. Rule 1, everyone wants 8. Bonding occurs when atoms bond with each other so that each can have 8 valence electrons. This can be done in different ways, either transferring those valence electrons or sharing them. We can first number our groups here, 1, 2, 3, 4, 5, 6, 7, 8, really drilling into our heads that these numbers or groups represent the amount of valence electrons of those elements in that group. We can use a few elements as examples. Chlorine has 7 valence electrons, and we know, according to our rule, that it wants 8. To get those 8 valence electrons, it would have to gain 1 valence electron. You may also argue that it could lose 7 to reveal a full octet underneath, ending at 2p6 neon. However, if we think about this logically, it would be much easier to gain 1 than lose 7. So let's look at magnesium, which has 2 valence electrons because it's in group 2. It wants a full octet as well, but it would rather lose 2 valence electrons to reveal a full octet underneath than gain 6. If you were to observe elements in this area, don't get confused by the transition metals and skip right over to 2 if you were to lose 1 electron. Remember that electrons are negatively charged, so when an atom loses that electron, it becomes more positively charged. It becomes a cation. So the number of protons would stay the same, but the number of electrons would be different. If an atom gains an electron, it becomes a negatively charged ion or an anion. Going back to our periodic table, we can see that groups 1, 2, and 3 would likely form the cations, or the atoms that would rather lose an electron, while groups 5, 6, 7, 8 would form the anions. Group 4 could either lose or gain 4 electrons, so they could be cations or anions, but they're more commonly cations. Cations and anions are important to understand when it comes to ionic bonding. Earlier we said there are 2 types of bonding: transferring valence electrons or sharing them. Ionic bonding is transferring valence electrons. In order for atoms to achieve their octet, a cation will lose valence electrons, transferring them so that the anion could gain those same electrons. That way both are happy and achieve their octet. That being said, that would explain why noble gases, elements in group 8, don't want to bond, because they are already happy with their full octet. On the AP Chem FRQs, though, you don't want to ever say that atoms are happy or satisfied because they don't have feelings. Rather, talk about stability. For example, chlorine needs to only attract 1 electron to have a stable energy level. If we use this idea of almost a mutualistic relationship between cations and anions, you could predict some ionic compounds by looking at the periodic table. For example, we know that transferring means what one atom loses, the other atom has to gain. So if I pick a random cation like magnesium will lose 2 valence electrons. So now I can find an anion that would gain 2 valence electrons. So that anion should be in group 6. I could pick sulfur, and I know MgS is an actual compound. Or we could pick something in group 7 like chlorine, but because chlorine would gain only 1 valence electron, while magnesium loses 2, I need 2 chlorines, so that again, what one atom loses, the others have to gain. So instead of MgCl, we would have Mg with 2 Cls. Now let's talk about bonding through sharing electrons instead of transferring them. This is called molecular covalent bonding. To achieve octets, each atom in the bond will count the shared electrons between them as part of its own valence electron. So here we have an example with fluorine. Fluorine is diatomic, meaning that it can't exist by itself as a single atom in nature. It will always appear as a diatomic molecule. So fluorine gas, oxygen gas, nitrogen gas, all of these elements require a 2 in the subscript. Unit 2 will go a lot more into ionic and covalent bonds, but that's all you need to know for now in this video about bonds. So back to Unit 1, we will now learn about the periodic table trends, thinking about the whole idea of atoms wanting to achieve an octet. Now that we've talked about bonds, we've really instilled in our brains that atoms are stable with 8 valence electrons. Atoms will add or subtract valence electrons to create complete shells if possible. This will help explain the electronegativity trend. Electronegativity describes how strongly an atom attracts valence electrons in covalent bonds. It increases to the right, or as the number of protons increases, and increases upward as the number of shells decreases. Except, remember that this rule doesn't apply to noble gases. So even if we would expect this trend to state helium as the most electronegative atom, it already has its octet. It doesn't want to bond with other atoms anyway, so it is not electronegative. Larger noble gases like xenon, though, are exceptions, but we won't get into that very much in AP Chem. So remember that electronegativity increases this way and this way. So, is fluorine or oxygen more electronegative? Well, fluorine is more to the right, and fluorine has more protons, so it has a greater positive charge, meaning that it would be more likely to attract valence electrons. In a different way, chlorine would be more electronegative than bromine. Not because of protons, because if we wanted to explain it with protons, bromine would have more protons and therefore be more electronegative. But if we're comparing atoms vertically, instead of comparing protons, we're going to compare shells. This is in the n equals 3 level, and this is on the n equals 4 level. If you have more shells, you're going to have more electrons repelling each other. Therefore, there's less attraction, and the atom is less likely to attract valence electrons. Another trend you need to know is atomic radius, the distance from the nucleus of an atom to its valence electron. As you gain protons left to right across the periodic table, electrons outside will be more attracted and pulled closer to the nucleus. Therefore, the radius will decrease. So as you increase protons, the atomic radius will decrease. Another factor that affects radius is the number of shells an atom has. We talked about how moving down from period 1 to 3 will increase the number of energy levels. By doing this, the effect called shielding increases. So the core electrons repel the outermost valence electrons, increasing the atomic radius. To sum it up, you can create these arrows to show the trend of increasing atomic radius. So if electronegativity increases this way, atomic radius increases the opposite way. Lastly, let's talk about the ionization energy trend. Ionization energy is also called binding energy, as we saw it before in the photoelectron spectroscopy practice problems. This is again the energy required to remove a valence electron from an atom in its first ionization energy. The next electrons removed will be the second, then third, then fourth ionization energies. So using Coulomb's law, which we discussed before, if the electrostatic force, which, reminder, is the attraction between opposite charges, is very high, you're going to need more binding energy to remove an electron from the atom. So its ionization energy would be greater. Well, which things affect electrostatic force according to Coulomb's law? Radius and charge. So ionization energy would have the opposite trend as atomic radius and the same as electronegativity. So the arrows would still go this way. And so to sum up those trends, electronegativity increases this way, ionization energy also increases this way, and atomic radius increases the opposite way. Another important thing to keep in mind about ionization energy is that there may be spikes in ionization energy. For example, going from 1 eV to 75 eV suddenly, if you are taking an electron from a stable atom. For example, it's easy to remove 2 electrons from magnesium. As we discussed, it can form a cation by losing 2 electrons to form a stable shell underneath. However, if we were to remove 1 extra, so 3 electrons, that would mean removing 1 more electron from an already stable shell. This is extremely hard, so the ionization energy, or energy needed to remove the electron, significantly increases. Using these spikes, or lack thereof, we can predict whether something was a first, second, or third ionization, or, in reverse, if we have a table with the first, second, and third ionization energies written, we should be able to predict which atom it was. Here, we have a table with the first, second, third ionization energies. We have 1, 2, and then suddenly 75. So we can predict that the third electron was really hard to remove, and that means we had to remove it from a stable shell. So take a look at this practice problem and try to predict which atom this table is based off of. We can use the periodic table as a number line and use jumps to justify our answer. So if we were to remove 3 electrons from neon, 1, 2, 3, that wouldn't be very hard. If we were to remove 3 electrons from magnesium, we would remove 1 here, and we will remove 1 here, and the next one we would be removing from 2p6, a stable subshell. And so that would be really hard to remove, so B looks like a good answer. And we can still check C and D. Chlorine is here, it wouldn't be too hard to remove 3 electrons, and same for chromium. So B is going to be our answer. We also keep ionization in mind when we think about electron configuration. Let's use one from earlier. If we look at magnesium's electron configuration, and a practice problem asked us, what happens if we remove 2 of its electrons with second ionization energy? We can use the periodic table almost as a number line and jump 2 spaces back. We end up with neon. Recall that if magnesium lost 2 electrons, it becomes a cation, and we say that it has a charge of positive 2. In this case, we say the magnesium ion and neon are isoelectronic, meaning they have the same number of electrons. Be careful not to simply say that magnesium and neon are isoelectronic. Only magnesium's cation is. If you wanted to write the electron configuration for this cation, write the original configuration, which was 1s2, 2s2, 2p6, 3s2, and subtract 2 from the outermost subshell, or typically the last subshell on the configuration list, which in this case is 3s2. That allows us to just completely erase 3s2, and with our new configuration, we can guide ourselves to p6. Let's draw the orbital diagram for this too. This is the original orbital diagram for magnesium, but if you were to draw one for its cation, you would erase those 2 electrons from the outermost shell, and if you were to remove those 2 electrons, there's simply no need for that 3s subshell. This is the orbital diagram for the magnesium ion. Recall that transition metals are a little different in terms of electron configuration. The same applies if you wanted to remove an electron. If we wanted to remove, say, 6 electrons from iron, you would think that we would just apply the same strategy as before. But again, this is not the case with transition metals. The electron configuration for iron was this. Because 4 is greater than 3, even if 3d6 is the last in this list, we'll first remove electrons from 4s2. Then, the leftover 4 electrons we still have to remove, we will remove from 3d6. So 3d6 will become 3d2. Our updated configuration will be this. If we were to remove more electrons, we would just continue by removing them from 3d2, 3p6, 3s2, and down the line. This applies with its orbitals as well. Again, if we want to remove those 6 electrons, we'll first remove 2 from 4s2, and then we'll remove the remaining 4 from 3d6. So this will become this. So this is my updated orbital diagram. Okay, if you made it this far, good job! To recap, we use concepts of bonding, mostly focusing on atoms achieving their octets, to realize the origins behind periodic table trends. Now that we ate the big frog, the final section of Unit 1 from me in this video will be mole-related ratios. This will set the foundation for Unit 4, which explores stoichiometry, and basically all the units, so pay attention. This is less concept-based and more memorization-based, but don't worry, you'll hear these ratios or numbers all the time, so it will be hard to forget them. First, we need to understand what a mole is. It's a unit of measurement in chemistry and allows us to relate amounts to each other. You will need to know Avogadro's number, which is the number of atoms, particles, molecules, ions, etc. within 1 mole. Avogadro's number is 6.02 times 10 to the 23rd. Don't worry, you'll accidentally memorize this. Another ratio you should know is that in 1 mole there are 22.4 liters of ideal gas at standard temperature and pressure, or STP. Earlier, we also talked about molar mass, or how many grams are present in 1 mole of an element. Well, if we're given a certain number of grams and divide it by molar mass, we should end up with how many moles that are in that sample. So we can switch between moles, grams, and molar mass. So if we have at least 2 pieces of these 3 pieces of information, moles, grams, and molar mass, we should be able to switch between all of them. Magnesium has a molar mass of 24.3 according to the periodic table. If we had a sample of magnesium that weighs 48.6 grams, we would divide this number by its molar mass. 48.6 divided by 24.3 is 2, so we know that our sample has 2 moles of magnesium. But I'll show you this on a train track to show you how that would make sense. We have a sample of magnesium that is 48.6 grams, and we know that this is magnesium. Then using train tracks, we also know that in 1 mole of magnesium, there are 24.3 grams. Make sure that diagonally your dimensions match. So if we have grams here, we should also have grams here, which is why I put grams on the bottom. I also know that I want to end up with number of moles, meaning that I want it to be on the top. So once I do this, I get 2 mole because I was able to cancel out the grams. So we know that our sample had 2 moles of magnesium. Let's do one for nitrogen. Let's first locate nitrogen. Nitrogen has a molar mass of 14 grams. If we had a sample of nitrogen that was 28 grams, we need to keep in mind that nitrogen only exists as a diatomic molecule. So even if we only have 28 grams of nitrogen, we wouldn't simply do 28 divided by 14 to get 2 moles of nitrogen gas. Instead, I'll use train tracks to show what we would do. So in our sample, we had 28 grams of nitrogen gas. Make sure to diagonally use the same dimensions diagonally. So for grams, again, I would put on the bottom. And we know that in 1 mole of nitrogen gas, there are 2 times 14 grams. So if we cancel out grams and we do 28 divided by 28, we will get 1 mole of nitrogen gas. We may have 1 mole of nitrogen gas, but we will still have 2 moles of just nitrogen in the sample. Using this information, we should be able to calculate things such as percent composition in a compound, empirical formulas, and molecular formulas. So let's get into percent composition. Before we do that, let's get the basics down. This is calcium nitrate. We should be able to count how many atoms of each element there are in this compound. There's a subscript here too, and this applies to nitrate, not calcium. Anytime there's double or triple or more of a polyatomic ion, like nitrate, there are going to be parentheses around that polyatomic anion. So calcium, there's 1 of it. But for nitrogen, we know that there are 2. For oxygen, we multiply 3 by 2, and we obviously get 6. So we are going to try percent composition for sodium chloride or table salt. So in this compound, we know that there is 1 of sodium and 1 of chlorine. So once we have established that we're going to find the total mass of sodium chloride, we know that sodium's atomic mass is 23 and chlorine's is 35.5, and in total we get 58.5 grams. I would usually use up to the 10th place for atomic mass. Now we're really close to finishing. All we're going to do now is divide the atomic mass of each element by the total. And for this I get 0.39, and then I'll just convert that to a percentage. So 39%. And for chlorine, I get 60.6%. It isn't exactly adding up to 100%, but that just reflects some differences in rounding. What if we have something like H2O? We know that we have 2 hydrogens and 1 oxygen. So that's going to change the process a little bit. So first, I'm going to get my total mass. And so I have to do 2 times the atomic mass of 1 mole of hydrogen, which is 1.01, plus 1 times the mass of 1 mole of oxygen. And if we do that, we'll get 18.02 grams. So now I'm going to divide what hydrogen contributes to the mass by the total mass. So hydrogen contributes 2 times 1.01 grams to the 18.02 grams. And if we divide that, we get about 0.11. And so that becomes 11%. So this compound is 11% hydrogen. If we divide what oxygen contributes over the total mass of the compound, we get 0.89. So that's 89% oxygen. And these indeed do add up to 100%. Now we can move on how to create empirical and molecular formulas. We can create empirical formulas based on a given percent composition for a compound. In this problem, we have a compound which is found to be 40% carbon, 6.7% hydrogen, and 53.3% oxygen. So what is the empirical formula? The first thing we're going to do is we're going to assume that our total sample is 100 grams. If we have a 100 gram sample, then based on the percent composition, we should have 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. Knowing each of these elements' molar mass, I should be able to find the number of moles in the sample. So in 1 mole of carbon, there are 12 grams of carbon. In 1 mole of hydrogen, there are 1.01 grams, and in 1 mole of oxygen, there are 16 grams. So if I do 40 divided by 12, I get 3.33 moles of carbon. 6.7 divided by 1.01 is 6.65, and dividing 53.3 divided by 16, I get 3.33 again. You're going to divide all of these moles by the smallest number. Out of all of these, the smallest is 3.33, so I'm going to divide everything by that number. When we do that, I get 1, around 2, and 1. So for carbon, I got 1, and this is 2, and this is 1. So I got 1, 2, 1 for carbon, hydrogen, and oxygen, and this just represents the relative amount of moles in my compound. And so when I make an empirical formula, I put down my constituents, and then I add the subscripts. And obviously, if there's a 1, you don't have to add anything. And this is my empirical formula. What if we were given a problem that told us that a compound had a molar mass of 90.12 grams per mole, and we were to find its molecular formula? Based on the empirical formula, we'll find the molar mass. The molar mass of carbon is 12.01, the molar mass of hydrogen is 1.01, and we multiply that by 2 because there are 2 hydrogens, and we add 16. Adding those together, we get 30.04 grams per mole. So if we had 90.12 grams as our molar mass of the new molecular compound, we're going to divide that by 30.04. If I do that, I get 3. So now 3 is going to be my special number that helps me get my molecular formula. All I'm going to do is take my empirical formula, and I'm going to multiply all of the subscripts by 3. And so if I do that, I get C3H6O3. And this is my new molecular formula based on these scenarios. We're done learning Unit 1. Let's do some practice problems. Let's do this FRQ I got from Fiveable. This is a photoelectron spectra and asks, based on this graph, identify the element and write the full electron configuration for it. You can pause the video and try to figure this out. I'm going to label my subshells first. So I have 1s, 2s, 2p, 3s, 3p. If you recall from earlier, this is one shell, and each one inside is a subshell. One shell would be n equals 1, n equals 2, and n equals 3, and within those we have our s and p subshells. Now that I have those labeled, I'm going to look at the y-axis, which tells me the relative number of electrons per subshell. In my first one, I have 2 electrons. I have 2 electrons again, and for 2p, I have 6 electrons. I have 2 here and 2 here. Let's look at what I end at. I end at 3p2. I'm going to go to the periodic table and find 3p2. I know this is n equals 1, this is n equals 2, and n equals 3, and this is a p subshell, 3p. I'm going to go 3 times, and I end at phosphorus. In response to part A, if it says identify, I just simply write the element, and then it's full electron configuration. Next, for part B, a student claims that the 1s peak, so this peak here, for sulfur, would be further to the right than the 1s peak of phosphorus. Is this correct? Pause the video and try to figure it out on your own. Here's phosphorus and here's sulfur. Remember, when we're comparing elements next to each other horizontally, within the same shell, we're going to compare the number of protons they have. Sulfur has 1 more proton. The student argued that the 1s peak for sulfur, which has 1 more proton, would be further to the right. If a peak is further to the right, well, what does that mean? It's going to have the same height, but the location would mean that it would require less binding energy for those electrons to be ejected, because the x-axis increases right to left instead of left to right. However, if sulfur has more protons, the electrons are going to be more attracted to the nucleus. Therefore, they would actually be harder to eject within that shell. Therefore, the 1s peak of sulfur would actually be more to the left than that of phosphorus. So it would actually rather be here. Is the student correct? No. Most FRQs will tell you to justify your answer. How would you justify your answer? Pause the video Sulfur has one more proton than phosphorus within the same shell. This means that its electrons are more attracted to the nucleus and would require more ionization energy to be ejected, rather than less. Alright, let's finish up the video with a few more practice problems. Why does an ion of phosphorus with a charge of -3 have a larger radius than a neutral atom of phosphorus? So pause the video and try to figure it out. Let's look at the periodic table. Remember that if something has a negative charge, it's an anion. It has become an anion by gaining 3 valence electrons. We gain 1 valence electron to become isoelectronic with sulfur, and then another electron, and then 1. So now I'm going to mark my suitcase green, and this is representing my anion. Going back to the question, it asks why my anion has a larger radius. But when we're comparing within the same shell, phosphorus has 15 protons, while argon has 18 protons. But don't get tricked, because you didn't actually increase the number of protons when you created an anion. You only increased the number of electrons, and the number of protons should have stayed the same. So what I would do is I would write down some data for each one. So my neutral phosphorus has 15 protons, and it has 5 valence electrons. My anion has 15 protons still, and it has 8 valence electrons. So we cannot explain this with protons. We cannot also explain this with the number of shells because they're within the same shell. So the only thing that we can say is that the electrons in the anion have a greater Coulombic repulsion than those in the neutral atom. So if we have more electrons, there's going to be more repulsion even within that same shell between the electrons. With more repulsion, there's going to be a larger radius. A compound is entirely made up of silicon and oxygen atoms. If there are 14 grams of silicon and 32 grams of oxygen, what is the empirical formula? Pause the video and try to figure it out. Something different in here that we didn't have in our previous empirical formula problem is that in this one, it doesn't give us percentages. So that removes a step for us because it's already in grams. So I'm going to take 14 grams of silicon and find how many moles are in that. And so in 1 gram of silicone, I have about 28 grams, and that leads me to get 0.5 moles of silicone. Let's do the same thing for oxygen. I have 32 grams of oxygen in my compound, and I know that 1 mole of oxygen has 16 grams. So that leads me to 2 moles of oxygen. Remember this important step. You're going to divide both of these numbers by the smallest number we have. So that's 0.5. For moles of silicone, we'll get 1. 4 moles of oxygen, we'll get 4. Now I'm going to write down my constituents and leave some space in between, and then I'm going to put my subscripts down. So this is my empirical formula. And if you got this, congrats. This is the next question. The diagram below shows the relative atomic sizes of 3 different elements from the same period, which is true. So I'm going to show you the 3 different elements. X is the biggest, then Y, then Z. These are the answer choices. A, effective nuclear charge will be greatest in element X. Effective nuclear charge is just talking about the charge of the nucleus, which we know it has protons, so it's positively charged. The first ionization energy will be greatest in element X. Remember, the first ionization energy is energy required to remove the first valence electron. C, the electron shielding effect will be greatest. Remember that shielding has to do with the core electrons repelling the outer electrons in terms of shells. And D, the electronegativity value will be greatest in element Z. And remember that electronegativity is the amount of force to attract an electron in covalent bonding. When you get these type of questions, remember the trends that we had. So electronegativity increases this way, ionization energy increases this way, and atomic radius increases this way. But go ahead and pause the video and try to figure it out on your own. If you got D, you are correct. So let's look at A. It says effective nuclear charge will be greatest in element X. If I have more protons in element X within the same period or the same shell, element X should be the smallest. If it has the most protons, the electrons are going to be pulled in the most. So I can cross out A based on my picture alone. B, the first ionization energy will be greatest in element X. So ionization energy being the greatest means that it's going to take the most energy to remove an electron. Because the atomic radius is big, the attraction between the nucleus in the middle and its electrons is weaker. We talked about Coulomb's law, which is Q1, Q2 over radius squared. If the radius is bigger, since it's inversely proportional to the electrostatic force, that force will be weaker, and so we can cross out B. C, the electron shielding effect will be greatest in element C. So shielding means that there are more shells, or there are more electrons. Because element Z is the smallest, we can cross that out. Also, the problem said within the same period, so we're not going to have a different number of shells anyway, so we can cross out C. Answer choice D says the electronegativity value will be greatest. Element C, I can already see that with our diagram with Z having the smallest atomic radius. It's going to have more attraction, more opportunity for attraction, and just looking at our trends too, if I have something that is going to be smaller, the opposite of increasing atomic radius will be here, it's also going to have the most electronegativity. D would be the answer. Now, the reason why I put this here is just to show that just because you learned a trend doesn't mean you're always going to use those arrows. Sometimes you don't even need to look at that to be evaluating your answers. It's good to have multiple options to solve things. You can see how I used this and looked at the diagrams and also sometimes used these trends. You don't want to just rely on one thing because sometimes you have these elements where you won't know what the exact element is, so you won't be able to spot it on the periodic table anyway. Instead, you'll have to use other clues. The next question says, which of the following is true about sodium and chlorine? A, sodium has greater electronegativity and larger first ionization energy. B, sodium has larger first ionization energy and a larger atomic radius. Chlorine has a larger atomic radius and greater electronegativity. Chlorine has greater electronegativity and a larger first ionization energy. Pause the video and take some time to figure that out. If you got D, you are correct. Let's look through the answer choices. And you can skip through if you're confident about how you solved it. A says sodium has greater electronegativity than chlorine and also a larger first ionization energy. So let's locate chlorine and sodium on the periodic table. It says sodium has greater electronegativity. I know that electronegativity increases this way, so there's no way that would be possible. It says it has a larger first ionization energy. Ionization energy also increases this way, so that's not possible. Sodium has larger first ionization energy. We already said that's not possible. C, chlorine has a larger atomic radius, so atomic radius increases this way. So I know that that can't be true, and so D must be the answer. We'll still check it. Chlorine has greater electronegativity, yep, and a larger first ionization energy, yep. The next question asks, approximately how many neutrons are present in a 10-gram sample of argon atoms which have a mass number of 40? So take some time to figure that out. Okay, so if you did this, you are correct. So if you took that 10-gram sample of argon and you put the same dimension here with 40 grams on the bottom, in 1 mole of argon, and you knew that there are 0.25 moles of argon in the sample, and you took 0.25 moles of argon, and you're trying to find the number of neutrons. Earlier we said we use Avogadro's number, which is 6.2 times 10 to the 23rd. And you can do that for particles, ions, electrons, protons, neutrons. If we get that number, we'll get approximately 3.3 times 10 to the 24 neutrons. The next question asks, in general, do metals or nonmetals from the same period have higher ionization energies? Why? Remember that metals are here. Metals are usually our cations. What form our anions are going to be our nonmetals. So over here, this staircase represents our metalloids. It says they must be from the same period. So let's compare a nonmetal and a metal within the same period. Let's look at magnesium and chlorine. Which one has higher ionization energies? You could look at the trend, but in an FRQ, you would not be able to say that the nonmetals within the same period would have the higher ionization energy because according to the ionization energy trend, ionization energy increases across a period and up a group. You cannot use a trend as a reason. You have to use a reason for a trend. Because they're within the same period, we're going to use their protons or their valence electrons since they're in different groups. So chlorine would have a higher ionization energy because it has more protons, so it would require more energy to remove an electron. If you also said that chlorine is closer to achieving a complete energy level, so it would have higher ionization energy, you would also be correct. The third to last practice problem we have is the ionization energies for an element are listed below. The element is most likely to be sodium, magnesium, aluminum, or silicon. So pause the video. If you got B, you are correct. So the biggest jump here we have is between the second and third ionization energy. It must have taken a significantly larger amount of ionization energy to remove the third electron. We actually did this earlier. We looked at the periodic table. We look at an element whose third electron would be really hard to remove. Elements in this group would work. Why? Because if we're removing one from here, the third we would be removing from a full shell. That would be harder to remove because it's stable. It wants to have 8. Magnesium would be the best answer, and you already did this earlier in the video. The second to last question is compare the radius of magnesium's cation and chlorine. So magnesium's cation, we're going to be comparing the radius of magnesium's cation when it loses 3 electrons. We're going to remove one here, and one here, so it becomes isoelectronic to fluorine. And then we have chlorine. We can compare these directly because they're not within the same period or shell, and they have a different number of shells. We can compare This is at n equals 2, this is n equals 3. Because chlorine has one more shell, there's more shielding between the core electrons and outermost electrons, so the atomic radius would increase. However, you should consider in terms of terminology that now that you have compared the cation of magnesium, you should say ionic radius to differentiate the radius of magnesium and its ion. Let's do an FR2 for an empirical formula. An experiment is performed to determine the empirical formula of a copper iodide formed by direct combination of elements. A clean strip of copper metal is weighed. Then it's suspended in a test tube containing iodine vapor, and a white compound forms on the strip of copper, coating it uniformly. The strip with the adhering compound is weighed. Finally, the compound is washed completely from the surface of the metal, and the clean strip is dried and reweighed. So to me, this at first sounds kind of intimidating because it's just so much information in this one paragraph. First, what's happening is they're weighing a clean strip of copper, and then they suspend it in a test tube. When they do that, a white compound forms on the strip, coats it, so now it's white. Then this strip is weighed. This is weighed, and this is weighed. And finally, the compound is washed, then it's dried and reweighed. This is my data table, so that mass of the clean copper strip before anything happened is here. And this is the mass of this copper stripping compound, and then this is after cleaning it. So A says state how you would use the data above to determine each of the following. You don't need to do any calculations. Well, I'm going to first start with copper because that's the most information I have. I know that copper reacted, and then I cleaned the amount of copper that had reacted from the solid copper, and I got this. And so if I subtract that from this, I can get the amount of copper that reacted. And so if I do 1.2789 minus 1.2748, I get how many grams of copper that reacted. Once I get the number of grams of copper, I can divide it by the molar mass of copper to get how many moles of copper that reacted. If I wanted to get the number of moles of iodine that reacted, I can just find the remaining difference. It says no calculations are needed, but I will just do some calculations here to show you what I mean. This is 0.0041 grams. And then I'm going to subtract 1.2874 minus 1.2789, involving these two numbers here, because if I cancel out this copper strip, I can know how much my compound weighed. And I get 0.0085 grams. And I know that this much of that was copper, so the other part of it must have been iodine. So I'm going to do 0.0085 minus 0.0041, and that's 0.0044 grams of iodine. Once I do that, I can convert that to the number of moles of iodine. B asks, how would you determine the empirical formula for the copper iodide? Remember how we created empirical formula before? We would take the moles that reacted. Let's say we had 3 moles and 4 moles. We would divide each by the smallest number of moles, so I would divide both by 3. I know that I get 1 here, and I get 1.33 here. Well, in this case, whenever you get something like this, you want whole numbers, so you're going to multiply both numbers by something that would take this irrational number and make it a whole number. So I'm going to multiply by 3 and 3. So this becomes 3, and this would become 4. This would be our empirical formula. Of course, these are fake numbers, so you would actually have to get the number of moles and make that empirical formula. Then it says explain how each of the following in this experiment would affect the empirical formula that could be calculated. A lot of Chem FR2s will tell you how would this mistake or how would this difference cause an error in the calculations of this whatever lab. So let's look at how we would explain that. Number 1 says some unreacted iodine condensed on the strip. If we did that, we're talking about condensed. That's probably from the vapor here. So that's extra iodine. So my mass of the copper strip in the compound is going to go up because it has that extra iodine. Let's say it was 1.288. What would happen to the empirical formula if that number was too big? Then I would calculate my overall iodine to be too big. That would change my empirical formula by increasing the ratio of iodine to copper in my empirical formula. Number 2 says a small amount of the white compound flaked off before weighing. This time, the second data point here will become too small. If it's too small, then I'm going to account for less of that white compound. My amount of copper is going to be the same, but the only thing that would decrease then would be iodine. The opposite would happen here, and now with my ratio of copper to iodine, now iodine's ratio will be too small. So here it was too big, and here's too small. That is the last practice problem for Unit 1 from me. I hope you enjoyed this video.